Thank you, Jules. So my chat today is about our higher order functions. But before I delve into that, I'll tell you something about me. But Jules kind of told most things already. So I'm a software engineer at Databricks. I work out of the Databricks Amsterdam office, and I work on Spark SQL and the performance of Spark SQL, mainly in the version of Spark we ship called the Databricks runtime. I'm also a Spark committer and a PMC member, and the latter means that you get to deal with fun things like adding new people to the project, but also voting for new releases. And in a previous life, and that's also where this comes from, I was a data engineer and a data analyst. So, complex data, that's basically one of the things we're going to talk about today. Spark SQL has like pretty decent support for complex data. So you can actually model complex structures and using a few primitives such as a struct. A struct is basically a fixed number of fields that have a name, that also have an order. And each field in the struct can have a different type, if you want to. You can also associate different other information like nullability and metadata, further metadata with each field. You typically access a struct by its name, a struct field by its name. Then you have arrays, and arrays are variable length, so they're a bit different than a struct. They contain the same elements over and over and over again, and each element can be primitive, so an int or a double or something like that, or more complex, like an array of an array. You can also do that. You typically access an array by its index. And then you have like a map. A map is a bit of half and half between the two. So you have key value pairs in a map. Each key should be unique, and that maps to a single value. So you can compare that to how you would access a field in a struct. All keys should have the same type, and all values should also have the same type. Please note, if you ever use maps in Spark SQL, they are a bit crippled. We are trying to fix that in the next major release, but that'll be another 6 months. The reason is that maps are unordered, and internally we don't have the correct methods to make sure that it works as key, for instance, as a key, because then you need to be able to check for equality and also do that in a relatively performant way. So these three primitives are actually part of the SQL 99 spec and the 2003 spec. So they've been around forever. Well, for ever, 19 years. That's pretty long in my book. But not many databases support them yet. The support is slowly coming. And so Spark SQL supports them. So with these three components, you can actually build tree-like data models, which are generally more expressive than flat data. I've called it flat Earth to annoy people. Multi-table designs where you denormalize everything and make structures like that. And that's, although those designs work, they are generally take a lot of effort and a lot of maintenance. And I think tree models are more expressive. So to show you an example, this is I think the canonical example of JSON data on the internet. I think it's a tweet. I managed to. It contains a couple of things. It contains a date when it was created, an ID, and I've came up with a nice text: looky nested data #Spark hashtag SSEU, and then it contains a couple of other things like a display text range, and that is an array of ints. It contains a user, and user is made up of an ID, made up of a screen name. It also contains something called an extended tweet. That's when you go over the old character limit. And that also contains a full text field, some display range information, but it also contains entities, and those entities are things like annotations of the tweet. So in this case, the only annotations we can make are the hashtags, so you have to hashtag Spark and SSEU. But these are all examples of nested data. So for instance, the hashtags are an array of structs, the entities is a struct, the extended tweet is another struct, and so forth and so on. And if you would parse this in Spark SQL, you would end up with something, a schema like this. So you have, which seems pretty complex, and it is. But it sort of also shows you that you can model and scope things very nicely using structured data. More and more data is written in this way, and that's just because it's a more natural way of doing things. And for the people who ask, why should I care? Well, if big data has given us anything, it's like a lot of data sources, and the fact that you tend to query on raw data more and more. So you, as an analyst or as a user of data, you are much more likely to have to work with nested data. So, and have to manipulate it. If you want to manipulate structs in Spark SQL, that's pretty easy. You can access the field names by their column names. You can create new structs by using the struct function, and you're pretty much set. However, maps and arrays, they are not that well supported. So you can actually get data from a map, get elements, and or from an array. But that's super easy to do. But let's say if you want to transform an array, if you want to add a field to a struct that's in an array, or do something more fancy, then you have like a very hard time doing that. You'll have to do some actual work there. And I'll show you a few examples of how you can transform or manipulate arrays and maps. So let's say we're transforming an array. We want to add 1 to each element in an array of an input table. So that input table has 2 fields, an ID, which is an integer, and a field named vals, and vals is an array of ints. So the row with ID 1 has vals 1, 2, 3. The row with ID 2 has vals 4, 5, 6. And all I want to do is add 1 to each element in that array. So to end up with something like this. So now ID has the value, the row for ID 1 has values 2, 3, 4. Well, that should be simple, right? Yeah, so the first approach, and I've seen this in practice quite a few times, is exploding and collecting. The first step with exploding and collecting, and you would, first of all, you would write a query something like this, and that is, you would first, the inner query is, you should start at the inner query, and that does select something from the input table, and then explodes all values. Exploding means that you instead will create a tuple for every ID and value combination. So in this case, we will end up with like 6 tuples, and then we're going to collect that values back again, and when we collect, we also add the value. So there was the explode, and the explode will do what I just said, and that is create like a flattened table, actually. So that's fairly easy, and then we do the collect, and collect list will collect a new list of, is an aggregate function, it will collect all the values of val plus 1 for that given ID. And that will look something like this. So this is fine, we have solved this problem, and I can stop talking now, right? What?
Will this keep the order correct?
No. So there's somebody's helping me here. So it has like, well, before we get to the ordering, it has like another problem. So we are doing a row level transformation, and if you explain that plan, it will do a file scan. Well, that's expected. It will do a generate and generate will flatten that data, and then we'll do an object hash aggregate. That's something that will collect the data, and then we do an exchange. And we have to do the exchange because we are aggregating, and the planner says, well, I don't know where those tuples are, so I need to make sure that the tuples with all the same IDs are in the same partition. And then it's doing another aggregate to make sure to create the final result. However, that exchange is super expensive. I am trying to change a value in a single row here. This shouldn't be that hard. And as this mister on the second row just told me, the ordering is not guaranteed here. So that might also give you some fun bugs to work with. There are actually a few more problems with this. So the keys need to be unique. So let's say I have 2 rows with the same IDs. Then I'll end up with 1 row with too many values. So those things generally are not that obvious, and it will take you an evening of debugging before you figure out that this is going on. Another fun one is this one. Values need to have data. Let's say I have a null in the values field. If you do this, you will end up with 1 tuple. So both are not great. So there's a slightly better solution here, and that's using a Scala UDF. And that requires you to write some coding, to do some coding. And also, by the way, you can do this in Python as well. That'll also work. So in this case, I'm defining add1. I'm taking a sequence of integers, and I'm producing a sequence of integers. Please note that the sequence of integers are Scala sequences. Spark internally uses a very different format, the tungsten format. So every time you call this function, you have to first translate everything from the internal format to a sequence, and then translate it back. In this case, it will be reasonably fast, but it is doing a lot of allocations, and that's just pretty expensive. And the add1 function takes that value sequence and does like a map over that value sequence and adds 1 to every element. So easy peasy. Then you have to register the UDF, and that's a bit more work. So you have to, well, give it a name. That's obvious because you want to have it work in SQL. And then you have to, well, at least, so this was what got me with this example, is then I have to really type it well to make Spark understand which type it will return. Otherwise, you will get a pretty interesting runtime error. We're trying to fix that as well. And then you can use the UDF just by calling select and then referring the UDF, and Bob's your uncle. So this is pretty good. It's much faster than explode and collect. And it does not suffer from correctness. It's just correct always. So if you want to do something here, prefer UDF over the previous construct. It also has some downsides. As I mentioned, it's pretty slow. You need to register UDFs per type. So and what I mean by that is that you have to, if you have like this thing that takes integers, now you also have to create one, and now you're changing your schema, and now you need longs. Now you need to write a new UDF. It's trivial, yes, but you still have to write that code, and you have to register it for that type, and it's very inflexible for that. It shouldn't, but I'll get back to that. No, you can just check for null, and then you're fine. So it is much correcter than the previous case. And it doesn't really work well with SQL workflow. So the thing is that now you need to start registering a UDF, and let's say, and then you need to, do you do that in Scala or in Python, and then you need to switch back to SQL, and that means you need to share sessions between different REPLs, and that's just a bit of work. So we should be looking for something more fitting here. Oh, it's also clunky. My point is that both solutions don't really look, they have issues. They're work. And the reason for that, generally, if you feel like that in software engineering, that is because you are missing like some structure or some primitive. In this case, we are missing primitives for working with such data. And so how we're going to fix that? Well, let's begin by taking a step back. We had option 2, right? The Scala UDF that had like one super nice thing going on there. It had like this map, and it had an anonymous lambda function. So the map is a so-called higher order function. Now, the problem here is that map is taken in SQL, so we cannot really name it map. But so we can name it transform. But otherwise, we are trying to do a similar thing. So we're trying to have like some higher order construct that'll give you some idea of how to transform that array and give you a function that will operate on elements. So we can do the same thing for Spark SQL. And so we named it transform. And the nice things here is that it's native to Spark SQL, no serialization needed. And it works for SQL out of the box. So it should be fast and should be easy to use, right? So how does this work? You have higher order functions. You have the higher order function, that is in this case a transform. And transform takes an input array, that's the vals thing, and an expression. And what it does is it iterates over the vals array and produces a new array in the same time. So it will apply the expression to every element in that array, and you will get like a brand new shiny array. And then you have the lambda function, and that is actually the computation you apply to each element. And you can divide actually the lambda function into two things. That's an argument list because it needs to know what you're doing, and it also takes and the computation you want to do. So there are a few more things. Remember how I said that data is nested and that people like nesting stuff and combining things together. So if you only have a higher order function that works on one level of nested data, then it's pretty much useless. So we support nesting of higher order functions as well. And there's another thing what's also kind of useful is that you can capture your context. So that means that you have in the higher level, you can refer to things in the computation that are defined in the previous level. So in this case, you have like the ref value on the top level, and in the transformation computation, you use that ref value and you add that to the value. Can I take questions later?
Can we do also some filtering, for example?
I'll get to that. Yeah, so that was the whole point, right, of this whole exercise. Yeah, they're faster. So I measured collect, explode, and collect, and that takes about 26 seconds to complete, which on, I think, 100 million tuples on a 10-node i3 4x large cluster, if you really want to know. I tried the UDF. UDF is quite a bit faster. It only takes like 5 seconds to complete, and then the higher order functions take 2 seconds to complete. Yeah, so this sort of drives home for me the point that it's a lot faster. Higher order functions will land in Spark 2.4, and we will ship the following versions. We have higher order functions for array types and map types. For array, we have the transform function. We just discussed that one. It just transforms an array and applies an expression to every element. You have a filter function where you can take an array and filter it by some predicate and produce an array that only with values that only match that predicate. You can apply. You can check for existence in an array. You can reduce arrays, so you can sum them or do some check summing or whatever. You can combine two arrays with zip width and then apply a computation on top of those. And for maps, we have basically the same functions, a little bit different. You can transform keys, transform values, also filter it, and also combine two maps together. So, and also, if you're going to use 2.4, it'll be out shortly, I think 2 more weeks, and then we have, it'll pass the vote, I think. Also, there are a lot of new collection-based expressions added, like creating ranges, in an array of a sequence of a sequence in. You also have shuffling and a few other things. It's pretty nice. It makes it a lot easier to work with these things. And finally, we should look at the future, what happens beyond Spark 2.4. So I think we have given quite a bit. We've improved life a lot for working with arrays and maps. However, so I said that structs are easy, and they are. I maintain that. However, it is if you have a really wide struct, let's say you have 50 fields in the struct, and you want to change one thing, you'll end up nowadays you are end up typing those 50 fields again, and and modifying the column you want. So I think we should be adding more, making it more easy to manipulate such structures. So, for instance, by adding by making the dataset with column work with nested data. So if you say with column A.B and then the expression, then it will update the field B in the A struct for that data set. And the same goes for renaming. And I also think we should add some struct fields for some methods on struct fields. So select, so you can make a subset, select a subset of things. Also with column command and with column renamed. So the disclaimer here is you guys are the first one to know that I think this is needed. So it might not land anytime soon. We are aiming for I am aiming for 3.0, but I still need to discuss that with other people and reach some consensus. And that concludes my talk. Are there any questions?
Thank you, Herman. So we got loads of time. Who wants to start with the high order questions, then we go all the way to the low level questions? All right, let's start with.
All right, thank you for pointing out the features in Spark SQL. So you said you didn't like the Scala UDFs, but you prefer writing UDFs in strings in SQL statements?
That's a matter of personal taste, but no, I don't particularly like, I do like typing in Scala and those kind of things, but the thing is that it's very limited to to people who have both those REPLs running and have like a proper isolation setup. And if I'm just a SQL analyst and I want to write that, then I currently am dead in the water. Yes, I like types, but I like usability a bit more. That would be my personal preference.
Sorry. I'll run back and forth.
So what is the fundamental difference between having this map and then providing as a UDF? Till now, I always have an understanding that it was good, I was using higher order function, but now you say, okay, in this Spark SQL, you're using again similar thing, but at the end of the day, it is still in higher order function, right? So what is the fundamental difference which kind of really improves this performance, let's say from 5 seconds and then to 2 seconds?
So the fundamental difference is that we can optimize through the higher order function now, and we can actually do much more performant code generation. So before you would have a Scala UDF, which is like a very opaque function to the JVM because it implements function something in Spark SQL, and you will end up, if you do that, you will end up with megamorphic call site and a few other things which make it slower and hard to optimize for a JVM. Whereas in this case, we can actually make it it's transparent for Spark SQL, and we can actually produce the code in line and get this speed up. Does that answer your question? So you're asking if we can reuse something. So in a way we did, right? So we are still using the same sort of syntax. You're still creating, combining functions in the similar syntax. The reuse part is not that easy because it's a fundamentally different thing. The JVM is general purpose, and if you want to have things run fast, general purpose is not your friend in many cases. You want to specialize in that case, and that's those two things bite each other.
Herman, got a question.
Sure.
So thanks for the talk. I've got a twofold question actually. Will you expose those higher order functions in the Python API as well? And if so, will you write Scala code within the SQL, within the Python code? Which sounds a bit weird.
It is currently a SQL construct, so you can, it works on columns. You are passing in an expression, so there is actually no Python or Scala. It's just actually SQL expressions what you're working with. So does that answer your question, your first question? It's not that I'm trying to nest as much languages inside of each other. That's again not the goal of usability. And as for Python, I have to be careful there because I think some things will work, but I'm not sure which ones. And I will have to talk to somebody who's a bit more knowledgeable about that aspect.
A question over there.
Hello.
Hi.
My voice is too high, sorry. I want to ask you whether you have thought about benchmarking these to vectorized UDFs as well. I know that there is a lot of ongoing work on that, but I think similar functionality can be kind of embedded to vectorized UDFs. And am I right about it?
So the vectorized UDFs are mainly a Python thing. First off, internally Spark SQL is just still a tuple at a time. So yes, I think at the end of the day we should integrate them. But that would mean in this case that you would have to move the map into Python and do the computation there. But sure, we can do something like that.
I thought that as it is, Pandas is supporting this kind of aggregations, collections, behavior.
Yeah.
So even now it should be working, no?
I don't know. I have to look that up.
I think there's a Jira open for that, but you might have to look it up. We will. Homework for us. Herman.
Yeah.
There was a question, a gentleman here. Yeah.
Hi, thanks for the intro. Question is, you mentioned that the higher order function construct is a fully SQL construct, so that means that the lambda code snippet that you write there is also, you fully parse it and you fully interpret it. Like, what are the limitations in like the language that you can use there? What mathematical operators can you use? What string operators can you use, and so on? Is it like limited by Scala or?
No, it's you can use every expression there is in Spark SQL, and here's the but: you cannot use subqueries. That's the only thing you cannot do.
Okay, thanks.
Okay, we have only time for last short, low-order question. Anybody?
I have to
You want to
run.
make me run? I think I'll make 10,000 steps on Fitbit today.
Hi, thanks for the talk. I just wanted to check if UDFs would be, it would be possible to apply UDF on the transfers, for example, instead of specifying a lambda. If you have like a nested higher order function at the bottom level, you would apply a UDF, and at the higher levels would apply lambdas.
Yes, you can apply UDF. You might still have to write the arrow and the little syntax, but you can definitely use UDF.
Okay.
All right, guys, give a big hand to Herman.